Hello everybody, welcome to Lecture 8. Today we'll be talking about pumps and the various kinds of pumps that you may find in your hydraulic systems. Note that this will be Chapter 5 in your textbooks. So getting started, let's jump back to our explanation and understanding of Bernoulli's equation. Right? And Bernoulli's equation is essentially a balance of energy. Right? At one point in your system, the fluid is at some sort of height, at some sort of pressure, and moving at some sort of speed. Then, in the other part of your system, you'll have it at a different height, a different pressure, or a different speed. And Bernoulli's equation is all about balancing these two, right? Now note that with no losses or additions of energy, the hydraulic fluid will always have the same amount of energy between the 2 points that we look at. However, Bernoulli's equation accounts for the fact that we can add or remove energy by introducing several of our H terms, right, or our heads, our pump head, our motor head, and our head loss, right? Head loss talks about energy being removed due to the friction in the pipe, due to heat coming out of the system, and all sorts of miscellaneous energy losses. And again, note that it's a minus, which indicates a loss of energy. But today we're going to be focusing on HP, or the pump head, right? The energy that is being added to the system in some form. Specifically here, the P stands for pump, right? And we see that it's a plus symbol, meaning that there is more energy, or there's energy being injected into our system from this pump. So, how do we actually find out how much energy is being added? And how this energy is added? Well, let's take a look at pump characteristics. Now, these pump characteristics will depend primarily on the type of pump that you are using, and the type of pump is primarily categorized by how it responds to pressure. So, to start off, let's first talk about a common misconception, which is that pumps pump pressure. That is not true, okay? Pumps do not pump pressure. They don't create pressure, all right? Instead, pumps produce a fluid flow, all right? They cause the fluid to flow through our system, and pressure, on the other hand, is created through a resistance to this fluid flow, right? We can see here that fluid flowing through our pipe here. We've got a little pressure gauge, and on the right, we have a little restriction here. Now, the pump has nothing to do with this higher pressure in this position and the lower pressure here in this picture. What is causing that pressure is the fact that we're trying to restrict the fluid flow that's coming from our pump, right? So the pump is just pushing these arrows, this fluid forward, and the restriction here is what actually creates this pressure. Now, pumps are classified primarily on how the pump actually responds to this change in system pressure, right? How does the pump behave when we do introduce a restriction like this, when we kind of pinch our hose, if you can imagine that, right? When we pinch our hose, does our pump give out? Does it have to work harder? Does it reduce the flow? Does it keep the flow? And to answer these questions, we classify pumps in two general categories. Those two categories being positive displacement pumps and non-positive, sometimes called dynamic displacement pumps. Positive displacement pumps will always displace or pump a fixed amount of fluid regardless of the outlet pressure. Right? If we take a look at our little diagram here, notice that regardless of whether we're lifting 2,000 pounds or a couple more than 2,000 pounds, you'll notice that the pump continues to push forward the exact same flow, right? Our 1 gallon tank flows or fills at the exact same rate, right? As we know, because of Pascal's principle, having this much weight on a piston creates a very high pressure, illustrated in the red here, versus having a lower weight creates a lower pressure, illustrated in this yellow here, right? But regardless of what the pressure is, you can see it also indicated on the dials here, this pump will continue to pump at 1 gallon per minute. All right, that's our positive displacement pumps. Note that the pressure limit here is usually around 12,000 psi, although there are specialized pumps that can go beyond that. Non-positive or dynamic displacement pumps will pump a variable amount of fluid depending on the outlet pressure. So again, looking at our little figure here, notice we have one system where the pressure is low, and then another system where the pressure is high because we've introduced a restriction. Right? We can see that for our dynamic displacement pump here, we are pumping a certain flow, and it's just flowing through our system normally, but when we introduce pressure, illustrated right here on the right, we can see the temperature of our pump goes up, becomes overstressed, and the flow slows down. Notice the arrow is moving slower, right? This means it is a dynamic displacement pump because when we add more pressure to the system, the pump struggles to keep its flow rate, and the flow rate actually goes down. All right, so there are your two broad categories of pumps. To get started, let's first talk about dynamic displacement pumps. Specifically, we're going to talk about the impeller type pump and the axial type pump. But before we go into the specifics, we have to point out one very important thing about dynamic displacement pumps, pertaining to how you actually install them, maintain them, and use them. And this is called pump priming. Now, some pumps require priming, which is defined as filling the pump and inlet pipe with fluid before you turn it on, in order for the pump to actually work. All right? And this is especially true for nearly all non-positive displacement pumps. Okay? So, if I were to simply buy one of these pumps and then drop a hose into some hydraulic tank and turn it on, this pump would not work because it has not been primed. Okay? To prime the pump, again, we would need to drop our hose into the liquid, but then also pour liquid into the pump itself, as well as the initial hose, for it to work. Right? As an example, for those of you in the microcontrollers class, this is how the pump works in that system. It will not work unless the hose is initially filled with water. Now, pumps work by creating a lower pressure at the inlet, which sucks the fluid up. Okay? Think of me going in for a sip of ice-cold Sprite cola from a little fast food drink can, right, with a straw. In order to suck that fluid up, right, I create a vacuum in my mouth, which brings the fluid up to my mouth, and I can drink my delicious Sprite. Now, positive displacement pumps, right, so not the dynamic displacement pumps, can use air as the medium to get the vacuum started, right? This is kind of like what I do when I drink my Sprite, right? When I suck in, when I create a lower pressure in my mouth, the fluid comes rising up and I can drink my Sprite. However, non-positive or dynamic displacement pumps cannot do this. They cannot use air as a medium to get the vacuum started. This would be like having to fill up my Sprite can and my straw, as well as my mouth, with some Sprite initially before I can enjoy more Sprite. Right? Non-positive displacement pumps cannot use air for the vacuum. So we have to actually fill the pump with air first, we have to fill the pump with fluid first in order to actually utilize it. Now, another important note about dynamic displacement pumps is that you actually don't have to regulate the pressure. Now, you still can, and typically you still should, but with dynamic displacement pumps, we remember that the core operating principle is that they will respond to an increase in system pressure. If I pinch my hose or I put too much weight on my piston, right? These types of pumps will not continue to produce flow. They will lower the flow until the load is too much or the pressure is too high, and the pump simply stalls out, right? Notice, so first up here, we have our impeller pump, right? The impeller pump works by having fluid injected in the center, then using these kind of strands here to sling it out to the side and push it out of the output. And note that there is a bit of a margin, a bit of a space between the propellers and where the outer chassis is, right? Where the fluid is able to kind of free flow out to the output. Conversely, down here in the bottom right, we have a positive displacement pump. Okay, so not the kind we're talking about right now. This is just an example. We'll take a deeper look at this in a bit. But this positive displacement pump works by taking water at the inlet, pushing it through these outer gears, and then pushing it out at the outlet. And notice there is no gap between the gear's teeth and the outer chassis, right? This means that when a positive displacement pump produces a flow, it can't produce a backflow, even if the outlet pressure is too high, right? It forces the fluid through. However, when it comes to these dynamic pumps, right, if there's too much pressure here at the outlet, it has the capability to push this fluid back through and back into the inlet here at the center. All right, again, we'll take a look at an animation of this guy in a moment here. So this is typical. This is a typical construction of dynamic displacement pumps in that their gears or the primary mover, that is the thing that is pushing the fluid, does not connect directly to the outer chassis, right? There's a bit of a gap to allow the fluid to kind of just be gently nudged through, not necessarily forced like it is in positive displacement pumps. Right? The margins allow the fluid to slip, so it can flow backwards if pressure is too high, but when it comes to positive displacement pumps, no margins means that even if the pressure will build, it will continue to pump, right? Which is why we have to regulate positive displacement pumps, lest you are fired from your job for causing a hydraulic explosion. Okay, so taking a deeper look at these impeller designs, impeller pumps, which are also sometimes called centrifugal pumps, work by using something called centrifugal or centripetal force, right? If anybody's seen the video of physics professors or such, where they'll take a bucket of water and they'll swing it around really fast, right, above their heads, and this creates the effect that the water kind of stays in the bucket even when the bucket is upside down, right? And we're going to take advantage of that by using that centripetal force to instead push water out from the center point, the inlet, straight to the outlet through the impeller blades, right? The impeller blades, you can imagine, push the water out from the center to the outside, and that water is then forced out the outlet, right? If I take a quick look at a little animation here, so water comes in the center, and then the impellers force that water to the outside of our pump, right? And as this impeller continues to force this water to the outside of the pump, eventually it gets pushed out of the outlet. Now again, notice how there's kind of a clean, there's no fixed spaces between the impeller blades and the chassis, right? The fluid can easily backflow from the outlet to the inlet if I put enough pressure on the outlet, which is why this is a dynamic displacement pump. In other words, if we put enough pressure on the outlet, it can cause a reverse flow for the pump, right? Causing the pump to overheat or hydraulic fluid to leak, right? So these are typically used in low power applications where you're not using a lot of energy, right? Again, right, the fluid flows through the inlet to the eye, which then gets picked up by the blades. The rotational force from the impeller pushes the fluid outwards radially. Right? We can see here it pushes it outwards, and then as the fluid builds up in this outer ring, eventually it's forced out the outlet. Here we can see a pressure versus flow curve of this type of pump. So on the x-axis we have the flow of this pump, and on the y-axis we have the pressure. So notice that at the maximum flow, right, if I push this guy up to its maximum flow, we get the minimum pressure. Or conversely, if I have some minimum pressure here, right, or below, the pump will just pump at its maximum flow rate. However, if I continue to increase the pressure on my pump, right, if I continue to increase the pressure at the outlet, I pinch my hose or I add more weights to my piston, the flow rate slowly starts to diminish, right, until I get to a maximum amount of pressure here, called the pump shutoff head, where the pump can no longer handle this amount of pressure at its outlet, and we get no more flow, right? So again, minimum pressure and below, right? In this range, you get full flow. Once you hit this minimum pressure, the pump slowly starts to slow down. It starts to struggle as you keep increasing the pressure, and eventually, at your pump shutoff head or max pressure, your pump will no longer produce a flow. Axial pumps work very similarly, however, they are in a straight axis and just push the water forward instead of this sort of radial approach, right? You can think of this as a motor on a boat, right? Or a ship, right? Axial pumps function the same way. However, instead of using centripetal flow, the axial pump directly pushes the fluid in line with the pump, right? So you've got your propellers here, an inlet, and as these propellers spin, it pushes the fluid through. Right? This shares almost all the same properties of an impeller type pump. It has to be primed, right? Obviously, if I just set this on top of some kind of fluid, right? If I literally just put this on top of a cup of water, this isn't going to pump anything, right? It either has to be fully submerged or it initially has to be filled up, but it cannot start with just air, right? We have to prime this. And it also experiences the same pump pressure response or outlet pressure response, where if on this side, right, on the outlet side, pressure builds too high, the propeller will no longer be able to spin, right, and the fluid might flow backwards. Again, just as a quick recap, remember that for dynamic displacement pumps, we have to prime these pumps, right? In other words, fill them up with water or hydraulic fluid before we actually do any pumping, and we don't necessarily have to regulate pressure because once these hit a certain pressure, they simply restrict the flow until there is no more flow. And we looked at two different types of these pumps, impeller and axial.